In example number 6, we want to find the zeros of the function 3x cubed plus 9x squared plus x plus 3. The title of this question says that we're going to have complex zeros. So we're going to continue to find the rational zeros using the rational zero theorem, which tells us that if p over q is a zero of the function, then p is a factor of 3 and q is a factor of 3. So remember that p over q is equal to the factor of the constant term divided by the factor of the leading coefficient. So the factor of 3 divided by the factor of 3. So the factors of 3 are plus or minus 1 and plus or minus 3. Now the possible values for p over q, and therefore the possible rational zeros for the function, are plus or minus 3, plus or minus 1, and plus or minus 1 over 3. And we will use synthetic division to evaluate each possible zero until we find one that gives a remainder of 0. Now in this example, they begin with negative 3 because it gives us a remainder of 0. But what that means is you're probably going to have to go through each particular factor to find out what that remainder of 0 is. So my recommendation is first do all the numbers, the whole numbers, before you get to the fractions to see if those numbers are rational zeros. So we're going to begin with negative 3. And so negative 3, and then we're going to write down the leading coefficients of the polynomial, which is 3, 9, 1, and then 3. And then we're going to bring down the value of 3. And so therefore, negative 3 times 3 is negative 9. 9 minus 9 is 0. Negative 3 times 0 is 0. 1 plus 0 is 1. Negative 3 times 1 is negative 3. And then we get that remainder of 0. And what that tells us is that x plus 3 gives us a remainder of 0. So negative 3 is a 0 of the function. So the polynomial can be written as, we have x plus 3, and then what we got for the quotient was 3x squared plus 1. So now we have x plus 3 and 3x squared plus 1. Now if we look at 3x squared plus 1, okay, we can't factor that. It's non-factorable. So what we can do is we can set that quadratic equal to 0 and then solve for x. So if we subtract 1 to both sides and divide by 3, so we have x squared, which is equal to negative 1 over 3. And then over here, we're going to get x, which is equal to plus or minus the square root of negative 1/3. And so we would have to rationalize the denominator like I did over here, which is plus or minus. We take out the negative to be I, the square root of 1 in the numerator, divided by the square root of 3. Now the square root of 1 is just 1, so 1 times I is I, divided by the square root of 3, so that's plus or minus I over the square root of 3. And then in red here, I'm rationalizing the denominator by multiplying the numerator and denominator by the square root of 3, which then gives us a result of plus or minus I times the square root of 3 over the value of 3. So what are the zeros? The zeros of the function are negative 3 and plus or minus I times the square root of 3 over 3. So if you take a look at the beginning part of the question, we notice that we had a degree of 3, which gave us 3 solutions. Now, if we look at the graph of the function in the figure, we will notice that at x equals negative 3, the graph crosses the x-axis, indicating an odd multiplicity of 1 for the 0 x is equal to negative 3. Also notice the presence of the 2 turning points. This means that since there is a third degree polynomial, we are looking at the maximum number of turning points. So the end behavior of increasing without bound to the right and decreasing without bound to the left will continue. Thus, all the x-intercepts for the function are shown. So either the multiplicity of x equals negative 3 is 1, and there are 2 complex solutions, which is what we found, or the multiplicity at x equals negative 3 is 3. Either way, our result is correct.